In this lesson, we're going to be looking at collisions involving momentum in one dimension. So by the end of this lesson, you should be able to explain qualitatively that momentum is conserved in an isolated system. You should also be able to explain qualitatively that momentum is conserved in one- and two-dimensional interactions in an isolated system. So basically, by the end of class, you'll have to understand certain aspects of Newton's laws that we learned in Physics 20 and combine them with momentum in certain interactions and situations and be able to make calculations. So let's go on to see what that means. So right here, conservation of momentum in 1D collisions. You need to know this definition here. To analyze these observations, it is important that first we understand what a collision is. A collision is an interaction between two objects in which a force acts on each other for a period of time. In other words, a collision provides an impulse to each object. So an impulse is a change in momentum. So anytime one object creates a change in momentum on another object, that is when we have a collision in 1D. So here is something for you to ponder. Now, why did cannons in the 16th and 19th century warships need a rope around the back tying them to the side of the ship? I want you to think about what we are thinking about here of momentum. I want you to pause the video and think of why they might have needed that. By the end of this class, you're going to figure out why that is, and you'll be able to answer this question hopefully pretty easily. So now, just before we get into what is the conservation of momentum, I want you guys to remember back to Physics 20 when we learned Newton's third law. For every action, there's an opposite and equal reaction. So the force of the action on something must be equal to the force of the reaction on something else. So right here, the force of B on A must be equal to the force of A on B. Now this becomes very important when we're thinking of momentum and collisions. Now let's go into the conservation momentum. Basically, the conservation momentum says the momentum before an interaction of two objects must be equal to the momentum after. So the net momentum before must be equal to the net momentum after. So let's take a look at this rocket here and combine those two things together. So we know before the rocket takes off, it's not moving. So its momentum is zero. It's 0 kilograms meters per second. Now, after the rocket takes off, the momentum must be equal to my initial momentum. Well, how could that be? The rocket's moving. Well, I look at this, if we're looking at our momentum after, we have the momentum of two things here. We have the momentum of my rocket plus my momentum of the gas. So we have momentum of rocket plus the momentum of the gas. So now you ask yourself, how could that be? How could the gas and rocket be equal to 0? Well, look at the momentum here of the rocket. It's all in the positive, and the momentum of the gas is all in the negative. So essentially, we're going to end up having this, we could rearrange it to make that equation there. And they will balance off to give me 0. So my question for you now is, why do you think I put a negative sign by the gas? Well, we look at that, we have the rocket going positive, and this is negative. So if I put a negative in front of the change of momentum, then eventually we're going to end up getting a positive. So a negative times a negative is a positive. Okay, there are 3 types of one-dimensional collisions that we will be studying and we need to understand and be able to do calculations for. The first one is explosions and recoil. Examples of this are things such as rockets, guns, and canoes. The second one is a collision where objects lock together and they continue moving. So this will be, we're going to see examples of trains, wrecked cars, and loading objects. The third one that we'll be looking at is our objects rebounding off each other. So this could be curling rocks, pool balls, rubber balls, and stuff like that. So let's first take a look at explosions and recoil. So let's take a look at our first question. Our first question is a recoil question. It says to calculate the velocity of an unconstrained rifle with a mass of 5 kilograms as it shoots a 50-gram bullet at a speed of 300 meters per second. So the whole idea here is we have to use Newton's third law, which is for every action there's an opposite and equal reaction. So the momentum of the bullet going forward must be equal to the momentum of the bullet going back. Another way of looking at this is saying my initial momentum of the bullet and the gun was 0. Therefore, my final momentum of the bullet and the gun must be 0 as well. So we know the momentum of the bullet, with Newton's third law, must be the same as the momentum of the gun. We also know that momentum is equal to mass times velocity. So now I'm going to isolate for what we want to figure out, and we're trying to figure out the velocity of the gun in this recoil. So I'm going to isolate for the velocity of the gun. Okay, now I'm just going to substitute in my numbers. Remember here, we had to convert grams to kilograms, and this is going to end up giving me a total of 3 meters per second backwards in the opposite direction of the bullet. So now let's look at our next question. In our second recoil question, we have a 75 kilogram hunter in a stationary kayak that throws a 0.72 kilogram harpoon at 12 meters per second right. The mass of the kayak is 10 kilograms. What will be the velocity of the kayak and the hunter immediately after the harpoon is released? So if we remember here, my net momentum, since the kayak is stationary before the harpoon's thrown, is 0. That means my momentum after, since conservation of momentum, the net momentum of the kayak and the hunter and the harpoon must also be equal to 0. So we start this off, we know my before must equal to after. So with that in mind, we know my total momentum of my initial, or before he throws the harpoon, is 0. And now I have two different momentums. I have the spear going that way, and I'm going to have the kayak and the hunter going another way. So then we know 0, a momentum of 0 kilograms meters per second, must be the same as the momentum of the canoe and the kayaker combined, plus the momentum of the harpoon. So if I rearrange this, I know the momentum of the kayak with the hunter must be equivalent to the momentum of the harpoon, but one is going to be negative. Now, let's just substitute in what is momentum. So one thing to remember is that the mass of the kayak is the same thing as the hunter plus the kayak. So now we want to solve for the velocity of the kayak. So I'm going to now plug in all my numbers to see what we end up getting. And this is going to give me a total of 0.10 meters per second. Now a key thing here is, since it's negative, we know it's going backwards. Or we could say 0.10 meters per second backwards. So now let's look at a couple of examples of some interesting one-dimensional collisions of objects that collide and lock together. So here's my first locking together example. We have a grandmother on roller skates going at 6 meters per second, roller skating down, and we have a child going at 0 meters per second. The grandmother then picks up the child and continues skating. We want to know what is the velocity of the child and grandmother after the collision together. So remember, our momentum before must equal to my momentum afterwards. Now looking at this here, my momentum before has two situations. There's two objects here that are in play. We have the grandmother and we have the little child. Now after, they are coupled together. So we only have the grandmother holding the child. So on this side here, we know the child is actually equal to 0 because he's not moving. So in other words, we have the momentum of the grandmother is equal to the momentum of the grandmother plus child. So now let's put in what is momentum. We are trying to solve for the velocity of grandmother. So we're going to rearrange my equation for that. So now, all I'm going to do is substitute everything I know. And that's going to give me a total of 4 meters per second right. And we have to make sure we have a direction here, because remember, it is a vector. And since it's positive, it must be going to the right. So here's another collision question with coupling. So a loaded railway car of a mass of 6,000 kilograms is rolling to the right at a speed of 2 meters per second when it collides and couples with an empty freight car with a mass of 3,000 kilograms rolling to the left at the same speed. What is their velocity after the collision? So by coupling, it means it locked together. So I want you guys right now to pause this video and try and solve this question. When you are done, then watch to see how I did it. So now that you attempted the question, let's see how well you did. So I'm going to start off by making a diagram to help me understand what's happening. So let's first make a diagram for the before. In the before, I have one train going to the right. And I have another train going to the left at the same speed. In my after, they couple together and they are both going to be moving, I'm going to assume, to the right because the right object has more mass. So let's set up my equations. We know the momentum before is equal to the momentum after. We know the momentum before, we have two trains. We have train 1 and train 2. And after, we have them both coupled together. So now we're going to isolate for what we want to know, which is my velocity after the collision. And then we're going to substitute in. Now just remember that it's to the left, so we have to keep a negative in there. Remember, velocities are a vector, which will end up giving us meters per second, and this is going to be to the right. We're going to look at our third style question, which is rebounding. So we're going to look at collisions and how momentum changes based on a rebound and how to do some calculations. These include curling rocks, pool balls, and rubber balls. Our first question is going to be with pool balls. So we have a billiard ball of 0.2 kilograms traveling at 1 meter per second east collides with a stationary ball of equal mass. The balls rebound. The incident ball travels at 0.3 meters per second west. What is the velocity of the other ball? So once again, we're going to set this up the same way. Our momentum before and our momentum after must be equal because of the conservation of momentum. So in the first situation, we have one ball moving and one ball at rest. Then these balls are going to collide and rebound off each other. So we're going to have now two balls moving instead of one. So my ball 2, we don't need to know in my before because the momentum of this is 0, so we can ignore that. So basically, I'm going to have the momentum of the first ball must be equal to the momentum of the sum of the other two balls. So now we're trying to figure out here the velocity of the other ball after. So we're going to figure this out here. So we're going to isolate for that velocity of ball 2 after the collision. Now in this case here, I know all my masses are equal because we said they are identical balls. So M2 is equal to M1. So in other words, my masses will all cancel out. So what I'm left with is the velocity of the first ball before contact minus its velocity after contact. So now I'm just going to substitute and see what we get. So one thing you must remember is this negative because it is going west. So altogether, we end up with east. So here's our last question. I want you guys to try this one by yourselves, and I'll quickly give you the answers at the end. So we have a 110 Stampeder football fullback moving at 1.8 meters per second east. He is hit by this Edmonton Elks defensive lineman that's 140 kilograms moving 1.5 meters per second west. After the collision, the Calgary Stampeder fullback is going west 0.25 meters per second. What is the velocity of the Edmonton Eskimo or the Edmonton Elks defensive lineman after impact? So my hint for this is make sure you know the directions of everything. Because remember, momentum and velocity, we need to keep our directions. So first line them up as we know that the momentum before must be equal to the momentum after. Then we're going to isolate for your Edmonton Elks linebacker. Then what you're going to do is you're going to substitute everything in. Now remember, anything that's going west is a negative. Everything that's going east is a positive. So let's pause this video and try and solve this question. Okay, welcome back. Let's see how you did. So first we did is we have to set it up. I know my momentum before must be equal to my momentum after. Then we look at this. We have two momentums on the before side. We have the momentum of the Calgary Stampeder plus the momentum of the Edmonton Eskimo. That's equal to my after, the momentum of the Calgary Stampeder plus the after the collision momentum of the Edmonton Eskimo. Now what ends up happening here, we have my velocity. We want to isolate for a certain velocity, and that is going to be this one right here. We want the velocity of my Calgary Stampeder, which is that right there. So we isolated for that here. Okay? Now, after isolation, we just plugged in all of my variables. Now, the key thing that we had to be very cautious of are these negatives. So anything that was going west needed to be a negative symbol. All right? Now, once we're done this, we end up getting a score, a velocity of 0.1107 meters per second, which is the same as 0.111 meters per second east. It's because my answer is a positive.